Hello, folks. It's me, Mr. Tuttle, as usual. Um, right now it is actually Wednesday morning, so I'm recording this a day early. Um, and what we're going to talk about today is friction, right? Now, one of the things that's a bummer, I guess, about the fact that we're doing this online this semester is that there's a couple things. One is normally we have a bit more time to kind of go through and think harder and do more cool stuff in class around all of the concepts that we've been discussing these past 5 or 6 weeks. But it is what it is, right? So we're kind of doing the best that we can. But this is one of my favorite subjects, and friction isn't like really necessarily an exciting topic. But there's some pretty cool math, and there's some, even though friction is kind of a common notion, like we all, know something about friction even before taking a physics class. Um, there's kind of a lot more behind it than you might think. Okay, and so that's what we're going to talk about right now. So let's see, I prepared some notes. And actually, before we even start to talk about friction, um, the reason why right now is a good time to begin this conversation is because at this point, we've done a decent amount of work with some pretty big concepts. So we've talked about momentum and impulse, right? Impulse and momentum, and more importantly, how there's this really close relationship between those two concepts. If an object has momentum, the only way that that momentum can change is if there is a specific impulse applied to that object, right? So those two concepts are kind of linked together. They're like cousins of each other in a sense. Um, the next two concepts that are really closely related is work and energy. And the connection between these two things is that if something has a certain amount of energy and that energy changes, the only way that can happen is if a certain amount of work is done to that object. So, or if you do work on an object, then you are giving that object more energy. So the amount of work done is equal to the change in energy of an object. So this is the concept that's especially important when we start to think about friction, because what friction is doing on objects when it's kind of doing its thing is it's doing work on that object, right? So as you push something across a carpeted floor, like a box or something, friction is doing work against you, right? At the point of contact between the bottom of the box and the surface of the carpet, right? We all kind of know that experience. Um, pushing a book across a table. You put an object on a tilted surface and it sticks there, right? All of this is about friction and friction doing work on that object, okay? Um, and so let's draw a quick picture, right? So here's a box, here's the floor. Let's say there's a force applied, meaning somebody is like pulling this box. Um, the force of friction, which is kind of like right here, right? Kind of, it's all happening at the surface of that box. The force of friction is always going to be acting in a direction completely opposite of the, I shouldn't even say the force applied. It's if the motion, right, if its velocity is going to the right, then the friction is acting to the left. Okay, so the force of friction is always exactly 180 degrees from the direction of the motion. So that's important. Okay. Um, let's see. Is there anything else? Oh, there's two different kinds of friction, right? So if you think about, let me see if I can get something cool here. Oh, this is one of my favorite books about physics. Put this book here, and I start, applying force and pushing, not too hard, but it's not hard enough to get it moving, and then eventually it starts moving. Now, it's really, really difficult to notice, but as soon as it started moving, as soon as this book kind of overcame that static friction, the amount of force that I need to push to keep it going at a constant velocity is just a little bit less. Okay, still friction, but there's two different types. So you have, let's see, static friction, which is friction that exists before movement. And then you have kinetic friction, which is the friction between moving surfaces. Okay? It's two different kinds of friction. One is always greater than the other. We'll talk later about which one is which, but maybe you already know based on something that I just said literally like 45 seconds ago. All right, so, let's see. Yeah, you can get a lot more complicated about friction because there's more sort of variables. Like, so for one thing, if there's two surfaces, like the actual surface area that you're dealing with has an impact on the force of friction. We're not going to get super detailed about it. We're going to kind of hit some of the basic highlights, and then if at some point in your lives you are, interested in learning more about this stuff, there are certainly other physics classes and in places you can go. You can take material science courses and things like that to really, really learn all there is to know about this stuff. Okay, but for now, this is good. Let me erase. Okay, so here's where we're going to get a bit more detailed about what actually is going on when we talk about friction. So I'm going to draw that basic box again. And let's assume that this box is on the floor at the surface of the Earth somewhere, and it has a certain amount of mass. So the mass equals m. The weight of this object, right? The weight or the amount of force that exists, right, between the surface of the box and the floor is going to be mass times acceleration. And the acceleration in this case is g, 9.8. Okay? So we know that there's going to be a force pointing down like this. Okay? Now, one of Newton's laws says if there is a force pointing down, then there has to be an equal and opposite force associated with this, and there is. We've got this. Okay? Now, this is a force that you can't really see, right? But it's there, right? Forces exist in pairs. And what the name of this force is called the abbreviation for it, or the symbol for it, is uppercase F with a little subscript n. And what that represents is the normal force. The word normal here means perpendicular. I don't know why they have like 17 different words for makes a 90-degree angle, but they do. Perpendicular, normal, orthogonal, all of these things mean makes a 90. So that's the normal force. We call it normal because it is perpendicular to the surface that's making contact here with the ground. Okay, that's the normal force. Okay, why am I talking about the normal force? Well, the reason why is because if we really want to understand what is this force of friction, the force of friction is equal to two things multiplied together: the normal force times, no, not K. K is the spring coefficient. That symbol right there. That symbol is a Greek letter. It's kind of like a weird, it's the name for this Greek letter is, well, it's spelled M-U, and it's pronounced either mu. You could say this is the Greek letter mu, or you can say it's the Greek letter mu. I like to call it mu, but there's two legit pronunciations for this letter. So it's either the cow or the kitten, whichever you prefer. Okay, So back to this. The force of friction is equal to the normal force times this mu. What does mu actually, like what does that symbol represent? Well, this is what we call the coefficient of friction, which we need because not all surfaces are the same, right? You all know some surfaces are way more slippery than others, right? So if you're trying to pull, a box along a cement driveway, a concrete driveway, that's going to be a different situation than trying to pull that same box across like a smooth hardwood floor, right? Two very different situations, and this coefficient of friction is the thing that kind of takes into account that different surfaces have different properties. Okay, so I think that's good for now. What I'm going to do on the next video is we'll do a few problems, a few practice problems around friction. And then after that, I've got like a little investigation where we determine the actual coefficient of friction of a few different surfaces. So that is it for now. Cheers.